FLINTPro system is the commercial implementation of the Full Lands Integration Tool, or FLINT. It is designed to be a complete online system for land sector greenhouse gas accounting, from the data storage, approach through land sector modelling, analysis, and reporting. Like the FLINT, the system is data agnostic and allows for varying degrees of data availability. It supports future data and model updates and increases in data product availability. There are three main components of the system, which are the input data stored within the cloud-hosted library, the modules, which are run using the FLINT, and the outputs. We're going to start here with the inputs. It is important to understand the requirements of data inputs in order to know what existing data sets are already available in your country or region and can therefore be incorporated into the FLINTPro system. In the absence of country-level or local data, FLINTPro is already configured to be able to simulate any region in the world using Tier 1 data and parameters from the IPCC Good Practice Guidelines. The first data type we will look at are the static spatial data sets. These can be in either a raster or vector format and define many of the parameters used by FLINTPro, such as the ecological zones, climate zones, soil types, and administrative areas. To demonstrate FLINTPro, we will use the country of Belize as an example. To show these examples of spatial datasets, I will be using QGIS, which is an open source, free GIS software. Here we have a spatial dataset from the FAO. This is the Tier 1 ecological zones mapped for Belize. It will be used as a FLINTPro input. If we interrogate this spatial dataset, we can see that the ecological zones have codes associated with them. Tropical rainforest, in this case, has the code 11 under GZ code. In a FLINTPro simulation, this code is referenced by a database to determine how to treat forests within this area. It is a classification used by the system to determine which growth rates, biomass values, and forest management regimes to apply to the forests in this location. The same spatial referencing process is used for soil types, climate zones, and forest management areas. The combinations of these will determine which parameters to apply to a particular pixel. This brings me to the next data type, which is the non-spatial data and model parameters. The data is stored within a SQLite database and can be viewed and edited within SQLite Studio, another freely available software. If we navigate to an example ecological zone, such as that with the ID 11, which we now know is tropical rainforest, then we can see the parameters that FLINTPro will use when simulating a pixel of forest in that ecological region. So we can see that the IPCC default maximum above ground biomass for tropical rainforests in Belize is 206.4 tons of dry matter per hectare of forest. If the national FREL or more relevant literature states a different value, then this can be changed in the database and re-uploaded to the FLINTPro data library. The final major input data type is time series spatial data. This category refers mainly to forest cover time series data. There are many different products available and many more being developed, commercial datasets, free datasets, at local, national, and global scales. FLINTPro can be configured to incorporate most forest cover time series products. It is currently configured with the Hansen et al. Global Forest Cover Dataset from 2000 to 2019. This is the Tier 1 default for FLINTPro. For Belize, we also have access to a commercial product developed by TerraPulse, which is a national level product that spans 1984 to 2021. We will later compare the usage of these two datasets within the FLINTPro system. Here is a visual example of what the TerraPulse Forest Cover Time series shows. As you can see, the forest is gained and lost through the years. The time series allows FLINTPro to identify pixels that gain or lose forest cover and apply the appropriate event sequence. For example, if a pixel gains forest in 2000, then FLINTPro will simulate the growth of forest on that pixel for the following years, accumulating carbon stock. If the pixel of forest is then lost on that pixel, FLINTPro will apply the relevant clearing or loss event and transfer the carbon stored within that pixel to a different carbon pool, such as the atmosphere or dead organic matter. Other time series data that FLINTPro can use could be wildfire and prescribed burning history, harvesting data, or other disturbance types. So these are the three main data types for a Tier 1 model within FLINTPro. If there is need for more complexity within the models or events, such as incorporating fire events or management regimes, different forest types, or different literature and parameters, FLINTPro can also accommodate these with use of their more sophisticated models. I'll now take you to the actual FLINTPro website so we can look at how all of these data products contribute to creating a FLINTPro simulation. For this, we'll also use the example of Belize. This is the landing page for the FLINTPro website. It's unique to each organization. From here, you get a summary of the simulations in the account. They are represented here by the icons on the map. So we can see that for Belize, there are 4 Belize simulations in this organization account. From here, you also get a summary of the simulations using this list on the left-hand side. So we can see that there's simulations for Belize and for Kenya and for Ivory Coast within this account. You also get a summary of the data library to see the major data sets within this account. An organization account is private and unique, so any data uploaded to this organization can only be seen or used by users that are registered to this organization. On top of this, you also have types of users which determine the permissions for each data set and the permissions for use within the account. That means you can have account managers who can upload data, download data, process simulations, and view simulations. And then you can have policy users as well, who can only view simulations that are published by those organization managers. This allows for privacy within the account and ensures that no important data sets are ever deleted or removed, and also ensures that any simulations can be approved by the organization managers or organization users. Within this account, as I said, you can see that there's a data library and run library. They can be accessed either from this homepage or from the menu on the left-hand side. First, we'll look at the run library, which shows a summary of all the simulations that are conducted within this account. So you can see the user that created the simulations, you can see the name of the simulations, the date that they were created on, the status, and the progress. So if there was a simulation that's not yet finished, you would see how far through this process it would be. As you can see, we can run Belize, and the runtime averages around 40 minutes. As the spatial extent and temporal extent increase, that runtime will increase as well. The visibility in this library will depend on the type of user. So as I said, we have policy users. They will only be able to see runs that are published by an organization user. So an organization user, once they've finished the final version or the new version of a simulation, they can click publish, and then that is then visible to all the policy users. That functionality allows non-technical policy users to be able to analyze the results and look at the simulations without actually creating any, and therefore clogging up the cloud processing. For Belize, we can see that there's a few runs here at the top. First, we'll look at the tier 1 run that was created with the data I showed earlier. So if we use this drop down on the right hand side, we can see a summary of the data sets that we used in this simulation. Over here on the left hand side, you can see it's got the configuration, and that's the Hansen tier 1 configuration. So that's a tier 1 configuration that is available for the entire world, specifically created for the use of the Hansen et al. Forest cover data. We have the database, which is what I showed earlier, which contains the IPCC good practice guidelines parameters for Hansen tier 1 configuration. We've got the forest cover regions, global regions, which are geographic identifiers for the world to ensure that the parameters we are using are those that are created for that specific location. Simulation area is the boundary of Belize. The forest cover data, the soil type, and the ecological zone data that we saw earlier, as well as the climate zone data. The output filters for Belize, we've used the AL4, the administrative level 4 boundaries, which is the sub-national boundaries for Belize. These output filters will allow you to disaggregate the results based on spatial filters. So if you have project areas or forest concessions or states, for example, then you're able to upload these as GeoJSON files and then use them as output filters. And we'll see later on when we look at the results how that contributes to your the output. We can also use this page to interrogate our data sets. So this is an important feature for data provenance. So if you're looking at a simulation that was conducted a few years ago and comparing that to your assumptions for simulations you're conducting today, you can use this drop-down database, click on your ecological zones, for example. That will take us straight to the data library, and it will summarize the library down to that data set that you've selected. And here we can see that we can either download this data set to interrogate it further within GIS software, or we can also see the description of the data set that was written on the upload of that data set. So it gives us a link to the data set and some summary of the metadata, as well as describing that it was created by the FAO. So as you can see, FLINTPro is really designed to be able to cope with long-term projects and supports the incremental improvement as new data sets, models, reporting requirements, and methods become available to the users. We understand that all users have different level of information. The system is designed to enable everyone. So it's already configured with the publicly available data sets to run any area of the world. As I described earlier, this is the Hansen data and the IPCC good practice guidelines parameters. Moving forward, each element of the system or each element of a simulation can be updated to create more accurate and relevant simulations and outputs. So for example, if you have a national forest cover data set, every year they will likely release the new year of the forest cover time series. This system enables you to first upload the updated data set and then rerun a simulation with that updated data set while maintaining that historical simulation. Data is constantly becoming of higher resolution and more readily available. The FLINTPro system is flexible enough to enable this improvement while maintaining the legacy of historical assessments and data. So as organizations transform and develop, the system records all the historical simulations. So for example, if there's a change in personnel or management, then there's a clear, concise record of all the simulations that were conducted by the previous management. To demonstrate how the system functions, we will start at the outputs that it creates. So these come in two distinct forms. The first is a database, which stores the carbon stock and flux information for each land parcel that was simulated. So the resolution of this is at the level of those spatial filters that I showed you earlier. So the smaller the polygons, or the smaller the areas that you include in your simulation, the more the higher the resolution of that output database. The second output is the high resolution spatial outputs, and these show the carbon stock, or the carbon stock within each of the carbon pools simulated for each year that was simulated. So there will be a raster file, and the pixels within the raster file contain the carbon stock for the pool within each year that you choose to download. So I'll show you what that looks like here. If we go to download on the right-hand side, new download, you can see here we can select the carbon pool, forest above ground biomass, for example, and we can choose the year that we want to download. And each of these years is a single raster file, the extent of which is the area of the simulation. So in this case, it'll be a raster file the size of Belize at the resolution of 25 meter by 25 meters. So I'll cancel that. Each of these can be downloaded, so you can download the database as well and query out your own data with SQLite queries. Although FLINTPro also has a business intelligence tool to be able to query out the information you need within this user interface. So, for example, it's highly useful to be able to download the rasters files so they can be used for within your existing processes, such as cartography or reporting, or combining with other spatial data sets that you have. So navigating over to the menu on the left, we have looked at the run library, we've looked at the data library. Within analysis, we can look at detailed analysis, and this takes us to our specially built business intelligence tool powered by Tableau. And there are many different ways of interrogating and viewing the outputs. So we can see that we can choose Belize Tier 1. It's quite a large simulation as a national run, but you can see once it loads, there you can see how the results are separated out into that sub-national data set that we saw, the AL4 boundaries. So these boundaries could also be interest areas, or project boundaries, or concessions, or administrative regions. So it gives you, that will allow you to disaggregate the temporal results, so the net change over time, or the carbon stock over time, by those spatial filters. So you can see what's happening within a plantation, for example. You can see what's happening within a carbon project. So if we then reduce these results down to the time series that we're interested in, so for this example, it's 1984 to 2021, and reduce the carbon pools down to the carbon pool that we're interested in. For this case, it's the above ground biomass carbon stock. Then you can see that we can see the total amount of above ground biomass in terms of carbon within Belize for that time series. We're then able to filter our results by our interest areas over here on the left. So one of these higher biomass areas down here, we can click on that, and that limits our results down to just that area. If, for example, you weren't interested in the total carbon stock within this area, but you were more interested in, say, the change in carbon stock over time, then we can change the results to show the flux values. So instead of the stock, we're now looking at the flux of carbon within those areas. So down here, we can again limit our results to this subnational boundary. And we can see that for this boundary, this is the flux of carbon in that area for that time period. So now that we've limited our results down to this subnational region, we can see that there's quite negative results for this area. It might be confusing to look at this chart and think that I'm saying negative results, but what we're actually monitoring here is the emissions. So the emissions is the negative changes in carbon stock, which is shown here on the positive axis. So you can see that the emissions has been decreasing through these years in 2017, and then increasing again with quite a substantial increase in 2021. We can also, this is obviously a combination of the gains and losses in carbon stock within this region. So we can actually also look at them separately and see, well, regardless of the net loss in carbon stock, what was the gain for that period? And you can see that the gain or the removals of carbon also increases in 2021. So that just shows that there's significant change. So despite there being quite a net negative amount of carbon removed from forests in this area, there was also quite substantial area of gains of carbon stock. So this is a really good way to look at the temporal trends of forest carbon change within these areas. We can see, well, within this area, over time, there's an increase or decrease in carbon stock. But what it doesn't give us is the spatial output. So where is this gain actually happening? If there's a net loss, where's the gain happening and where is that loss happening? So to understand more about the spatial trends and the nature of these changes, we need to look at the spatial outputs. Like all of the outputs, as I said, they can be downloaded at 25 meter resolution for the entire simulation area. And then you can look at it in combination with other data sets that you have, like the locations of projects, that sort of thing within GIS software. But FLINTPro also offers a method of viewing the spatial outputs within this interface. So if we navigate again over to the left-hand side here, and we click on visualization, this will take us to interface which has converted the raster files that I was talking about into a video tile to present there on the right hand side. So if we scroll down here to the simulation that we're interested in, we will look at Belize with the national forest cover data. So that's the TerraPulse data that I was talking about. And then we can look at the forest above ground biomass pool in terms of carbon in a visual format. So as you can see, there's quite a stark line in the biomass. The dark green is a higher biomass than the light green. And as you can see, it's quite constant with this stark line. Now, if you remember, that is the line that traces those ecological zones. So this simulation is at the resolution of the input data. So if you had more specific ecological zones and you were modeling more forest categories at different rates, then that would start to reflect the landscape more accurately. As I said, this is a tier 1 simulation, so it's only categorizing the entire forest landscape into 2 ecological zones. So in order to look at more closely at these results, what we can first do is apply the spatial filters. So again, for this is the AL4 boundaries. And here we can apply the spatial filter that we applied to the temporal data, and it'll appear here on our map. So as you can see, it buffers and the higher resolution data appears as you zoom in. So if we zoom in on this area here, you can see that if we change this data to represent what was present in 2001, you can see there's quite a lot of forest cover, quite a lot of high biomass forest. And then to identify the change between 2001 and 2005, we can jump to this year. And you can see that in this area here, there's quite a lot of forest loss, which leads to biomass loss. but then we also knew that from the temporal data, we also had forest gains, or we had carbon gains within this forest somewhere. And down here, you can see that between 2001, this area here we're looking at, and 2005, that's representing carbon gains within that area. So those pixels that are white have very low biomass, but it's non-zero. So that's probably a very young forest. And then that will slowly accumulate through the rest of the time series. So what this allows you to do is to, it gives more context to those output values. For example, if there is a forest regeneration or reforestation project in this area somewhere, we can view these in the context of the broader landscape. So firstly, are they actually accumulating carbon? What years are they accumulating carbon? How do these compare to the surrounding regions? And therefore, are they less vulnerable to forest loss? What's going on around them? So it gives an insight into whether you should be looking at doing risk analysis, but it's viewing your results in a spatial context. This data, to be able to better represent the differences on a better color ramp or color scale, then you'll need to download those raster files and upload them into a GIS software to be able to further look at, well, what's the difference between this pixel and this pixel over here.